Welcome to our deep dive into the fascinating world of gravity. You know, that force that keeps your feet firmly planted on the ground and prevents you from floating off into space. Today, we'll explore everything from the basics of this fundamental force to its mind-bending effects on the fabric of space-time. So, what exactly is gravity? At its heart, gravitational force is a fundamental attraction between any two objects with mass. That means you, me, your phone, even that coffee cup across the room, all exert a gravitational pull on each other. The more massive an object, the stronger its gravitational pull. And just as importantly, the farther apart two objects are, the weaker the force between them. Now, you might have heard the terms gravity and gravitation used interchangeably. Think of gravity as the specific case of gravitational force here on Earth. On the other hand, gravitation refers to the broader concept of this force acting between any two objects with mass anywhere in the universe. It's the force that holds the moon in orbit around Earth, the planets around the sun, and even galaxies together in vast cosmic structures. Like any other force in physics, we can measure gravity. We quantify gravity using a unit called meters per second squared, written as ms2. Here on Earth, that acceleration due to gravity is approximately 9.8 ms2. This means that for every second an object falls, its speed increases by 9.8 meters per second. Our understanding of gravity took a giant leap forward thanks to the brilliant mind of Sir Isaac Newton. He formulated the law of universal gravitation, which elegantly describes how this fundamental force works. The key takeaway is that the strength of the gravitational force between two objects depends on two things: how massive they are and how far apart they are. Now things start to get really interesting when we introduce Einstein into the picture. His theory of general relativity revolutionized our understanding of gravity, revealing its profound effects on the very fabric of space-time. One of the most mind-bending predictions of general relativity is gravitational time dilation. This theory states that time actually runs slower in stronger gravitational fields. Another intriguing aspect of gravity is the speed at which it travels. When massive objects move around, they create ripples in space-time known as gravitational waves. These waves propagate outward from their source, carrying energy and information about the event that created them. And guess what? These gravitational waves travel at the speed of light. Now, for all its cosmic influence, gravity is actually the weakest of the four fundamental forces of nature. Despite its weakness, gravity is the force that shapes the universe on the largest scales, from the formation of galaxies to the orbits of planets. The other three fundamental forces, the electromagnetic force, the weak nuclear force, and the strong nuclear force, are all much stronger than gravity. For instance, the electromagnetic force is responsible for electricity and magnetism, and it is what keeps electrons bound to atoms. While the other forces operate at very small distances, like within atoms, gravity acts over vast cosmic distances. This means that while the other forces dominate at the microscopic level, gravity's influence becomes significant on a macroscopic scale, and because it's always attractive, it has the ability to accumulate over massive objects, giving it a dominant influence on large scales. This is why gravity is the force that governs the motion of planets, stars, and galaxies, despite being the weakest force at the particle level. So if gravity is a force, what exactly is it a force of? What is pulling on what? Well, Einstein's general relativity provides a revolutionary answer. Gravity isn't a force at all. Instead, Einstein showed us that gravity is a consequence of the curvature of space-time. Gravity's influence is all around us, shaping the universe as we know it. It's the force responsible for the rhythmic ebb and flow of tides, caused by the gravitational pull of the moon and the sun on Earth's oceans. Gravity is also the cosmic sculptor, shaping the formation of stars and galaxies. It causes clouds of gas and dust to collapse, igniting nuclear fusion and giving birth to stars. Have you ever wondered what would happen if gravity suddenly ceased to exist? It's a thought experiment with some rather dramatic consequences. Without gravity, the Earth would immediately disintegrate. the same fate would befall the Sun and all other stars in the universe. While we can't see gravity directly, we can certainly observe its effects all around us. Scientists have developed incredibly precise instruments to study gravity and its effects. For example, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detects gravitational waves, those ripples in spacetime caused by the acceleration of massive objects. One common misconception is that there's no gravity in space. But the truth is, gravity exists everywhere in space. It's what holds the International Space Station in orbit around Earth and governs the motion of planets, stars, and galaxies throughout the cosmos. The reason astronauts appear weightless is that they're in a state of freefall. The story of Sir Isaac Newton and the falling apple is one of the most famous anecdotes in the history of science. It is often said that this simple observation led to one of the most profound discoveries in physics. While the exact details of the story are likely apocryphal, it illustrates the key insight that led Newton to his groundbreaking law of universal gravitation. This law fundamentally changed our understanding of the universe and how objects interact with each other. Legend has it that Newton was sitting under an apple tree when he saw an apple fall to the ground. This seemingly mundane event sparked a series of thoughts and questions in his mind. Newton realized that the same force that caused the apple to fall must also be responsible for keeping the moon in orbit around Earth and the planets in orbit around the sun. This realization was revolutionary as it connected the motion of celestial bodies with everyday occurrences on Earth, unifying the heavens and the earth under one universal law. Mars, our planetary neighbor, has long captured the imaginations of scientists and science fiction enthusiasts alike. As we continue to explore the red planet, it's essential to understand the gravitational environment we'll encounter. Yes, Mars has gravity, but here's the catch: its gravity is significantly weaker than Earth's. In fact, the surface gravity on Mars is only about 38% that of Earth's. Earth's gravity is what keeps us grounded, literally. It's the force that holds our atmosphere in place, dictates the flow of our oceans, and influences the very shape of our planet. The average gravitational acceleration on Earth is about 9.8 meters per second squared. However, Earth's gravity isn't uniform across the entire planet. Factors like altitude, latitude, and the distribution of mass within Earth can cause slight variations in gravitational acceleration. It's natural to wonder, where does Earth's gravity end? The answer is both fascinating and counterintuitive. Earth's gravity extends infinitely. The Moon, our celestial companion, has a gravitational pull all its own. However, its gravity is significantly weaker than Earth's, about 1/6 to be precise. This weaker gravity is why astronauts who walked on the Moon were able to bound across its surface with such ease, despite wearing bulky spacesuits. While the Moon's gravity may be weaker than Earth's, it still plays a crucial role in our planet's systems. As we've explored in this cosmic journey, gravity is a fundamental force that governs the interactions of objects on a vast scale. It is the invisible hand that shapes the structure and behavior of the cosmos, influencing everything from the smallest particles to the largest galaxies. From the fall of an apple to the motion of galaxies, gravity's influence is all around us. It dictates the orbits of planets, the formation of stars, and even the path of light as it travels through the universe. We've delved into the intricacies of Newton's law of universal gravitation, which elegantly describes the relationship between mass, distance, and gravitational force. Newton's insights laid the groundwork for our understanding of how objects attract one another, and we ventured into the mind-bending realm of Einstein's general relativity, which reveals gravity to be a consequence of the curvature of spacetime. This revolutionary theory has transformed our comprehension of the universe, showing us that massive objects can warp the very fabric of reality itself. Thanks for joining us on this journey through the wonders of gravity. We've covered a lot of ground, from the basics of gravitational force to the mind-bending effects of general relativity. Remember, gravity isn't just some abstract concept confined to textbooks and physics classrooms. It's a fundamental force that's constantly at work, shaping the world around us in countless ways. Don't forget to like, subscribe, and hit the bell icon for more fascinating science content. See you in the next video.